So we'll switch to the next session. This is a special session, as I had indicated in the program. So let me introduce some of the speakers. So just to give a background, so this is one of the recent NSF-funded AI Institute called ICICLE. We'll go over more on that. There are many people involved here. This is a multi-year project, 5-year project, $20 million from National Science Foundation. One of the 11 institutes funded in this round. Last year, they funded 7 of them. And it involves like 14 different organizations, 46 faculty members. But here, the broad focus you will see on the combining HPC and AI with applications. So we wanted to have a special session here just to inform the community and also looking for opportunities for collaboration and all. So in addition to me, we have 3 other presenters here and panelists. Professor Vipin Chaudhary, he is the chair of the computer science department at the Case Western Reserve University. He has been in this HPC for many years. Dr. Amitava Majumdar, he is the division director of the Data Enabled Scientific Computing Division at the San Diego Supercomputer Center and also associate professor in the Department of Radiation Medicine and Applied Sciences at the UC San Diego. And Joe Stubbs, he leads the Cloud and Interactive Computing Group at Texas Advanced Computing Center, which focuses on building cloud-native applications and infrastructure for computational science. SIC develops, deploys, and maintains multiple national-scale clouds as part of ongoing projects funded by the NSF. And so I just wanted to make a little bit this introduction short so that we'll have more time. Let me share, we have a set of slides and a very nice video. We'll start with that and then go into a short presentation. And then after that, we'll have some question answers. So let me share the other slides. The screen?
Yes, it's coming up.
Okay. So this project is called ICICLE, Intelligent Cyberinfrastructure with Computational Learning in the Environment. So there is a website here, which is the ICICLE.ai. So you can...
Sorry for the interruption. Can you disable screen sharing and start it again? It's still not coming up.
It's not coming up.
Or it's completely blank for me. I don't know if there is a...
I think it... Okay, so let me start...
Yeah, okay, now it's coming up.
Okay.
And DK, if you remember to share sound.
Yes, I have done that. I have done that. Can you see now everything?
Yes, Dr. Panda.
Okay. So this is the ICICLE.ai. So please take a look at it. It has a lot of information. Here we'll be presenting very short overview here. ICICLE stands for Intelligent Cyberinfrastructure with Computational Learning in the Environment. It is a very heavy acronym, but you will see what it means. So there is a video here. Let me play.
Policymaker wants to know how land use policies will affect a region's biodiversity. A farmer is concerned about how new weather patterns will affect crop yield, while food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities. Current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber infrastructure integration with AI just doesn't exist. Enter ICICLE, Intelligent Cyberinfrastructure with Computational Learning in the Environment. ICICLE is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with the flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. ICICLE will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The ICICLE conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay? Upon confirmation, ICICLE would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, distributors, transportation networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions from a baseline and alternative logistics that maintain consistent food supply for vulnerable populations, and estimate supply chain disruptions based on historical and current data from other locations, mindful of privacy. ICICLE will go even further by accessing high-performance computing centers to backcast and learn how reconfigured landscape-scale precision agricultural production and distribution systems could integrate with alternative supply chain infrastructure to avoid similar future disruptions. Using an orchestra of smart cyber infrastructure elements, ICICLE produces a symphonic answer that improves outcomes for diverse stakeholders. ICICLE holds the potential to transform today's AI.
I think it got cut a little bit, but anyway, I think it was almost at the end. So thanks for listening to the video. Hopefully, this gives a very broad overview. So here the idea is again at a high level. If you see, we are trying to propose a national infrastructure that will enable AI at the click of a switch. As you heard some of the examples, if you go back like a power distribution or like currently our iPhone, we expect a lot. Over the years, a lot of things have progressed. You just type things and things happen behind the scene. But that is not happening now with respect to some of the examples. If you you saw that supermarket example, or think of like a farmer standing in the field is trying to take a decision whether to harvest today's crops or not. So can the farmer just ask the question in the iPhone, and a lot of background things happen. It gets the stock market, it gets the weather, whether it is to be try to do the appropriate models, takes care of the current crops value. So all those things happen, and in the end, he or she gets an answer. So that is the kind of the futuristic things we'd like to do, so that it will be an integrated plug and play approach. And of course, there is a lot of security issues, transparent issues, computing issues, and the objective of this institute is to address these pressing societal problems. So at a high level, we have these are the kind of the main thrust: cyber infrastructure for plug and play AI, intelligent cyber infrastructure, the fields AS to HPC and cloud, and of course, there is a lot of focus on broadening participation in computing, workforce development, and especially for this institute, we have identified some of the collaborators focusing on 3 use case scenarios like smart food sets, animal ecology, and digital agriculture. But the ideas, whatever we develop, will be applicable to a lot of newer disciplines. Of course, we have the broad goals on education and outreach, as well as collaboration and knowledge transfer. So there is a very wide range. The team, coast to coast, I'll not go into more details, but very quickly, like a RPI, Delaware, CWRU, OSU, OSC, Indiana University, Wisconsin-Madison, Iowa State University, TAC, SDSC, UC San Diego, University of Utah, UC Davis, UC California, University of California Davis, and IC Foods. And then you can also see on the border a lot of collaborators of the national labs, research institutes, and also some international collaborations, and also collaboration with several of the other NSF AI institutes. So this was the overall leadership team. I am the overall PI. Vipin is a co-PI here, and we have other co-PIs from OSU. Then for each of the things, component like we have foundational systems AI, intelligent cyber infrastructure, collaboration knowledge transfer, CI development, co-design for the user-inspired science, BPC, and education workforce development, we have dedicated leaders. So the broad overview, as you saw from the promotional video, like the currently plug and play characteristic exist in current generation electricity and power grid. But if you take a lot of examples of the modern scenarios, like a food distributor or farmer, such capabilities don't exist. One has to really spend hours and hours trying to put together all these different components to get the results out. Sometimes it takes days and months. So the challenge is, can we democratize AI in these modern scenarios? And while we advance in the research, can we also assemble computational and human resources needed to build the next generation cyber infrastructure like a 2030 capable of supporting this AI across diverse user cases? So we have a lot of these goals, as you can say, plug and play AI, CI for AI and AI for CI for AI. We'll go into that a little bit more details. And also advances in foundational AI, how to design and develop model commons, how to design and develop conversational AI, privacy preserving AI, and adaptive AI. And in many of these things, we have our collaborators in the use-inspired domains. So we'll be actually working in a co-design manner to really have an end-to-end solution. That is the kind of the broad vision. So here, if you take a look at these examples, like I talked about the farming, you can think of like a smart food set, especially in this pandemic. You know, there are a lot of things you hear every day. The food shortage is happening. A lot of food is being destroyed or wasted. Logistics are not able to transport the food to the right place. So those are the issues. Similarly, in the animal ecology, the entire ecological environment, how the animal population is changing, how that is affecting the environment. So these are some of our very broad goals to really work to have an end-to-end solution. So this slide shows the things at the bottom. If you see, like starting from a field, if you have a sensor, just like I indicated, like the farmer example, the farmer might be carrying an iPhone or a drone might be running from there. How do you take really the data, do the processing at the edge, near edge, cloud, HPC, and data center, and really working with the upper level computing infrastructure and then the models and the AI components to provide the end-to-end solution. So the key value propositions are, we are trying to establish a national cyber infrastructure, develop the rubrics for training the next generation researchers, integrate emerging AI technologies, design a roadmap. And we basically, this institute will be like a nexus of collaboration among the cyber infrastructure, AI, and domain science folks for the next 5 years. And we have a very robust plan here to carry out the design because the technology is changing so fast. So we have actually a very concrete plan of, you can see on the left-hand side a spiral graph that is like the virtuous cycle. So as we keep on enhancing our different components, you can see like as we put it in the top, today's AI is tomorrow's CI. So you come up with some good algorithms, you come up with some good hardware, or even a firmware, that becomes the tomorrow's CI. But then using that tomorrow's CI, you can develop AI, and then again, that becomes the next year's CI. So we'll be going that kind of a virtual cycle support to make the solutions very robust, and at the same time, trying to bring it to the market. So with this, let me hand it over to Vipin. He will cover some of these motivations in more detail.
Thank you, DK. Can you hear me?
Yes.
Okay, terrific. So let's circle back to one of our use cases highlighted in the introduction by DK, the smart food sheds. So currently, posing a complicated question involving heterogeneous data sources would not be feasible for a food supply chain manager. So while she has data experience, searching for and applying appropriate AI models requires facing a crazy set of choices of how to proceed. And the current marketplace solutions may approach part of the problem, but a comprehensive solution is not currently possible. Next slide. So our vision with ICICLE is to democratize AI by facilitating the navigation of modeling choices through adaptive, environment-aware AI. By engaging interactively with the user, we can help them navigate or automate modeling choices, provide supporting evidence, interact with models and data in heterogeneous contexts that may require privacy and provenance tracking. Next slide, please. So in considering our 3 use case scenarios that DK had alluded to, we have identified a number of heterogeneities from computational environments to interfaces that require abstractions at different system layers. Many of the core elements of the research program center around defining and investigating these abstractions. And by considering these abstractions jointly within the Institute, we'll have many different perspectives from AI, from CI, and use case experts that can lead to innovative solutions. Next slide, please. So in the next few slides, we will summarize the key research elements in the center and how they relate to our scenario. So you see a few different colored boxes here. So the foundational systems AI research investigates key technologies. Let me turn my light back on. It's a motion sensor based light. So the foundational systems AI research investigates key technologies to provide interactive, adaptable, reusable, privacy preserving AI. As research in this area matures, it becomes part of the cyber infrastructure. Intelligent Cyberinfrastructure creates innovative infrastructure solutions that support AI computation from fields, edge to the data center. And co-design of AI for use-inspired science ensures that the solutions pursued have generalizable impact. Next one, please. So as alluded to before, ICICLE will advance 5 foundational system AI areas: knowledge graphs, model commons, adaptive AI, federated learning, and conversational AI. All these carefully selected areas, they embrace and aim to address the full complexity and heterogeneity in the environment-bound, edge-to-center, and user-supporting scenarios targeted by ICICLE. These systems AI capabilities, together with ICICLE's Intelligent CI, they form a first-of-its-kind, holistic, and highly synergistic CI system to enable plug-and-play AI. More specifically, we will advance multiple frontiers of knowledge graph research to support its central role in ICICLE. We will explore novel knowledge graph formalisms such as multimodal and spatial temporal knowledge graphs to represent the rich types of data that ICICLE will support. Automated knowledge graph construction is another important venue for innovation. And finally, we will investigate knowledge-based reasoning techniques, a central problem of AI that could enable a wide range of prediction capabilities. And such learning on large-scale knowledge graphs poses a huge challenge on efficient training. And ICICLE is uniquely positioned for this challenging problem because of its powerful compute and data infrastructure. It will in turn drive CI innovations to support large-scale distributed model training. For model commons, we will explore innovative research areas such as how to precisely profile AI models, how to flexibly compose AI models into scientific workflows, and how to track the versioning and provenance of AI models. Now, a pervasive challenge preventing this wide adoption of AI today is the discrepancy between the training and test conditions. which poses great generalization requirements on AI. Adaptivity to different application contexts that are possibly changing over time is central to ICICLE's plug-and-play vision. We will explore how to make AI context-aware, interactive, and continuously learning from use. We are also interested in auto-compression and distillation innovations that allow AI to run on different edge computes. We will also explore decentralized learning via federated learning to reduce the reliance on a central compute infrastructure while also mitigating data privacy concerns. And finally, we will develop conversational interfaces to our knowledge graphs and model commons to make both data and AI models more accessible. We will address research challenges such as how to efficiently bootstrap or adapt a conversational interface for new domains, multimodality, and adaptivity. Next slide, please. So let me briefly cover the research plan for CI for AI. So an emerging food agency manager comes up with the question, how could dozens of supercell tornadoes spreading over the Great Plains and Midwest impact food supply chains over the coming months? She communicates the question with conversational AI, which translates the original question to predicting future states of your regional supply chain under forecasted weather scenarios. Then, by consulting the knowledge graph and model commons, ICICLE decides to apply a model that predicts disruption under weather scenarios and mitigation by reconfiguring landscape scale precision agriculture production and distribution systems. And to train such a model, it needs a periodic access to satellite images, inventory data from producers, processors, transportation networks, wholesalers, and retailers. These entities would not like to share data with others. So ICICLE has to preserve the privacy. And since the satellite data is updated every night, the model may itself need updating every couple of days. The initial model should be ready within 2 hours with a validation accuracy of, say, 80% historically. The emergency food agency manager needs the prediction within 10 minutes. He or she also enables provenance to track how a decision is reached. CI for AI will take this requirement description and accordingly provision resources in heterogeneous hardware, software, platform, and network connections. And this CI for AI makes the complex decision transparent to end users by abstracting these resources like the hardware, software, platform, and so on in a uniform way. Next slide, please. The upstream applications, they interact with CI for AI via the control and coordination module, which is based on TAPIS that Joe will cover shortly. TAPIS will provide the resources and it will provision resources and manage the services for training, data management, inference, and data transfer. Now, for example, TAPIS takes the pre-trained model, the model to train, training frequency, and deadline to provision just enough resources in network bandwidth, the compute node, and data management service to launch the training and guarantee that the deadline is met. And so looking deeper into CI for AI, high performance model training addresses the CI complexity in hardware, software, and platforms. The data management addresses the data requirement heterogeneity in provenance, privacy, and integrity. The edge intelligence addresses various requirements in privacy and inference latency. And edge wireless deals with network complexity to address data transfer needs. The functional and performance heterogeneity in upstream applications is what the CI for AI addresses. And all of these research outcomes in AI for CI for AI, we talked about the cyclic aspect to it, will be incorporated into ICICLE without changes on the user side. And with that, I will pass on the baton to Amit.
Thanks, Vipin. DK, can you hear me?
Yeah.
Okay, good. So somehow my video is not working. So instead of trying to debug it, I think I'll just continue.
Yeah, no, sure.
Maybe I'll just turn off my video also. So yeah, thanks, Vipin. And so now here for AI for CI, we look into how AI techniques can be used to design CI to run in a range of applications that we will have, which will have different resource needs, given the variety of the applications. And the AI techniques will obviously focus on enhancing performance, elasticity, scalability, and the overall management of the CI, as we've been talked about. Various parts of the CI tracks includes the applications, middleware, and systems. And for the applications, we will develop user data-driven approaches. And that is, learn how application performance can be modeled in a general execution environment agnostic manner. And our middleware, our self-driving middleware will be based on typical machine learning frameworks such as TensorFlow, PyTorch, and it will optimize the end-to-end AI workloads. And we will use optimization techniques which will result in reducing computational manual overhead needed for hyperparameter tuning, for example. And the system stack will provide resource management and scheduling for HPC, cloud, and edge computing, which is needed for various applications, which may run in batch mode or in a long-running services or the latency-sensitive applications of conversation AI. So, for example, it may provide transient cloud VM such as EC2 to reduce cost of running applications. So here, research involves data-driven scheduling and fault tolerance using learning algorithms. And the edge wireless will involve distributed learning and optimization to provide reliable real-time communication as required by drones in the field, in agriculture, or maybe even in animal ecology case. And the cross-cutting themes relate to data-driven approaches requiring new mechanisms and interfaces for collecting and transmitting information all throughout the stack. So advances that will be made in knowledge graph and model commons will capture performance and resource profiles of our heterogeneous CI. And another theme is obviously the intelligent performance modeling and optimization, for which we will develop various black box and gray box models and for predicting performance all throughout the stack. So considering both the overall CI for AI and AI for CI, there is a synergy across the various AI and CI components and the virtuous cycle that DK and Vipin talked about. So AI research will help optimize CI, which in turn will provide the necessary tools to develop AI for CI models and knowledge graphs. So here we have one example. There will be various research topics, of course, just like for the CI for AI. But one example is this intelligent primitives, where we will have a product which is a portable, usable, high-performance library that will learn from hardware, network, and data. And this can also be used at the back end of other AI systems. There will be various other research topics under AI for CI. Next slide, please. So now we'll briefly talk about the privacy, accountability, and data integrity and the visual analytics. So next slide, please. So in ICICLE, we'll carefully consider and integrate privacy, accountability, and data integrity in order to derive scientific insight through AI, and that will be trustworthy by the researchers and end users. That's a very important, with any AI, as you can see here nowadays, trustworthiness and fairness is very important. So for privacy, to provide full control to data collectors or owners of their local data sets, we'll propose the use of personal clouds. That will be for each data collector, where he or she can store data coming from different sources in different partitions, example, namespaces of their personal clouds. And for data exchange between data collectors or between a data collector and data aggregator, we'll define and implement fine-grained, for example, attribute-based and dynamic access rights from one data collector personal cloud to others. For data movement and sharing, we will explore security, multi-party computation, and homomorphic encryption-based techniques, along with differentially private federated learning techniques to process data and share it in a privacy-preserving way. To enable greater open science for the ICICLE community, we'll develop privacy risk quantification and transparency tools. So, for example, these tools will inform data owners about the benefit and potential consequence of data sharing decisions. It will take into account how the data will be processed. For example, is it federated learning? Is it sharing the whole or part of the data? or just sharing statistics about the data, depending on the data provider. And it will also inform data owners about the privacy enhancing techniques used in the process, whether it's homomorphic encryption or secure multi-party computation, etc. And it will also inform privacy preferences of the data collector. For accountability, we propose deep AI audit trails, which is a collected resource of system and application information that will penetrate deep into the CI stack and expose information about potential casual flaws. We will also explore integration of deep AI audit trails into the ICICLE knowledge graph for rich contextualization. For data integrity, we'll develop techniques to look information about the credibility, integrity of the shared data to the data collector in an anonymous way. We will develop mechanisms to transform diverse and potentially noisy data streams, corresponding to different events into usable and reliable data. Next slide, please. Okay, so for visual analytics is an interface between the end users and developers of ICICLE and the AI and CI components. We will focus on using vision analytics to visually monitor the performance of AI and CI components and understand how AI and CI interact with each other and follow the logic of how AI models reach the decision that they achieve. And we'll see the virtuous cycle of how do AI and CI components adapt to the environment. And so visual analytics is going to be a multi-level, multifaceted, and multimodal approach to collect performance numbers from the entire ICICLE system, ranging from the servers to the edge. And it will analyze and monitor different facets of the system and pay special attention to the heterogeneous and dynamic nature of the environment that we will have. It will support the interface and visual output of a wide range of devices, from mobile to high resolution displays that we'll have near the servers. And importantly, it will interface with conversational AI as the natural interface to the users. And to protect the privacy of data as well as model, visual analytics will be tightly coupled with privacy layer using secure multi-party computation and homomorphic encryption. So visual analytics and PADI, the privacy, accountability, and data integrity will play very closely with each other. I think next it will be Joe from TAC who will continue.
Great, thanks Amit. I'll try to run through these quickly. So yeah, next slide please, DK. So it's clear that ICICLE requires, a generalized software infrastructure to integrate and coordinate all of these various capabilities. Some of the essential requirements are listed here. It's things like scalable cloud and HPC data management, high performance model training, dynamic resource provisioning, which Vipin alluded to, etc. Next slide, please. So instead of writing all of this from scratch, what we decided to do was build upon the TAPIS framework. So TAPIS is an NSF-funded API platform for reproducible research computing. It's a mature software. It's been used by dozens of projects, including multi-institutional efforts funded by agencies like NSF, NIH, DARPA, CDC, and NASA. And so everything you're seeing on this slide here, TAPIS already provides, a production-grade capability. Next slide. So on this slide here, we're depicting the complete ICICLE software architecture, basically. So existing TAPIS components that will be enhanced are shaded here in the light blue color, and then some new components to be added from scratch in the sort of orange. So for example, we'll add new APIs, brand new APIs to TAPIS to provide support for some of the fundamental AI abstractions. These are things like knowledge graphs, model commons, conversational AI. We'll also add a dynamic resource provisioning capability. We're really excited about extending TAPIS to the edge with this lightweight edge gateway server you see here in the corner, and that's going to allow us to do the low latency inference. So I think in the interest of time, I'll end it there, but I'm happy to discuss any of this in more details. So I hand it back over to you, DK.
Yeah. So thanks again, Vipin, Amit, and Joe. So just to conclude, again, this is a very large project. We wanted to bring only some parts of it. to give a high-level overview. But just to end, the broad objective here is the ICICLE it will try to enable the global leadership. It integrates into the national CI ecosystem. It will be integrative and interoperable. It will try to leverage existing recognized capabilities of multiple centers of excellence, other AI institutes, and large facilities. And it will be collaborative. So this is where we are actually trying to share these things with the community, at least the MUG community here, which are very much focused on high performance computing and cloud and machine learning. So there will be a lot of collaboration opportunities. If people are interested, please feel free to contact us, and we'll be trying to see at what level we can get engaged with you. So the broad objective is not just for research, but research to have translational impact, and that's what we want to carry out. So with this, let me close it here. If there are any quick questions or comments from others, we'll be very happy to answer as a team. Any questions from audience? I don't see anything on the Slack channel.
When is the project starting?
It will be the official start date is November 1st. So we just got awarded. So it will take a few months to get things settled, and officially will be starting in November 1st, another 2 months.
I have a question.
Sure.
Are you also going to do the hyperparameter optimization for finding the parameters of like finding the training parameters or the network, like layers and these things?
Multiple of those. Here, just like here, we talked about like the one component in the middleware. We have hyperparameter optimization. It can be applicable to multiple components of the entire software stack.
Okay, thank you.
Any other questions, comments? Okay, so if there are no other questions, we can close here. Again, this was just an overview, and please go to ICICLE.ai. So we'll be continuously updating it there. And once again, this is a big project we are starting for people. Again, if there are interested people, we are looking for, once again, strong students, staff, programmers. There will be a lot of people will be needed here. So if you are interested in working in any of these components and all, please feel free to contact any one of us.